Okay, maybe we can start since I think it's already a bit past the normal time, and I guess looks like quite a smaller group today, so I don't know what to make of that, but well, that's what happens sometimes, so hopefully I've not scared everyone off. I think we can start just with a couple announcements. First off, for this exercise number one, we realize it's been quite challenging. So if you haven't been following in Slack, the deadline's been extended to Wednesday at 5 o'clock. So you have a bit of extra time to work on the first exercise, which means also that tomorrow in the exercise session, if you still have questions about that, you can get some extra help there. So that's hopefully beneficial to you. Haven't extended the deadline for exercise 2 yet, but we'll see how the progress goes. It's sometimes hard to gauge whether this is, I don't know, going to take more time or not. I think it didn't seem to be that it would take a whole bunch of extra time for exercise number 2, but we'll see how it goes on Tuesday. The other thing that I was going to mention is we do have another course assistant, Alexei, who's not yet here. I don't know whether he'll join us this morning, but he may pop in. But you'll see him on Tuesday, so now there's 2 course assistants, which means also that if you come on Tuesday and you're worried about not having people have enough time to come and talk to you, you shouldn't worry about that too much, because there should be, well, twice as much in terms of the course assistant workforce, so hopefully that's beneficial to you as well, that you can get some extra time with them. Maybe I could also ask if there are any questions about the exercise number 1 at this stage, that, like, if you have general questions you can ask now. Otherwise there'll be a fairly short kind of introductory lecture for the topic for this week, and then there'll be time for you to get started on the exercise. So you could also ask, if you have specific questions, you can ask then at that time. But are there any general questions about this exercise 1?
Yeah, you know when you go plot through the last plot, problem here or something, there's like an arrow which comes up, which I think wrote, there seems to be like there's no new way to go or something.
There was, yeah, I don't know. I haven't seen, or I don't remember seeing that for the plot. I know that you can get an error message to come up if you, depending on how you do your dropping of the NA values, you can get error message to come up that way. But we can take a look maybe at what your code was doing. Yeah. Any other general questions? How many of you are mostly finished with the exercise 1? Is anybody totally done? A few people. Okay. So that's good. I sort of had the sense that not everybody would be done, and as a test of who's paying attention in Slack, I just posted the message in Slack about the extra time. So maybe some of the people who aren't here are freaking out about not having finished the exercise, but that could be a nice lesson for them in learning to follow Slack, because that's where our course communication happens. I don't mean to be a sort of dictator like that, but I don't like to sort of spread the communication around a bunch of different places. It's pretty much all in Slack. Any other issues with this exercise 1? If not, let's turn our focus then to where we are today. This is lesson number 2 for the course, and we're going to kind of continue in the theme of geostatistics this week. What you'll see is we basically have 3 small topics that we're going to talk about, and they all relate to various ways in which you can compare data to some kind of prediction. So we'll look at least squares regressions, which is basically fitting a trend line to data, like you maybe have done this in Excel. If you have XY data, you can put a trend line in there. We'll look at how you calculate that, because that's a useful thing to be able to do in Python. There are other tools you can use to do it, but the code is not that complicated to do it ourselves. Then we'll look at linear correlation. So this basically is a measure of how well your data fit to a line. So if you've seen plots where there's a trend line, you'll often see like an R value or an R squared value on the plots. We'll learn how to calculate R, and if you know how to calculate R, calculating R squared is simply the R value squared, so it's quite straightforward. And then we'll look lastly at goodness of fit. So these are measures of how well some data are fit by some kind of model, and we'll do this again in the context of fitting a regression line. So those are the three topics, and then the exercise, of course, you'll basically have three problems that directly relate to those three topics. These are all sort of basic statistical skills, but they're very useful and broadly applied, so it's, I think, a handy thing to learn how to do. For the lesson today, there's no notebooks or anything for you to follow along with, so you can, if you go to the lesson pages, you can, I think if you launch the CSC notebook, you won't actually get anything, but if you open them in Binder, you just get this text here, so there's not really any kind of Python cells or anything. But yeah, we can move to the first topic about least squares regressions. And basically, this is just one way in which we can fit some kind of model, in this case a line, to some point data. So you can consider, for instance, the example here of the weight percent SiO2, so how much silicon there is in a magma versus the temperature at which the magma erupts. And so what we see, generally speaking, and I think pretty much from the first year geological processes courses, you would see that as the temperature goes up, generally that will reflect magmas that contain less silicon, or in other words, the more silicon you have present, the lower the temperature of the melting and the lower temperature of the magma as a result. So in this example, this is just a figure out of a textbook on, I think, Geostatistics Explained or something like that. You can follow the link that's here. But you can see these data very nicely fit a line. So this is not a set of points where there's a line connecting the values between the points, but rather these would be temperatures that were measured for magmas, and then the composition was assessed by the weight percent SiO2. And this is the line that best fits the data. In this case, it's pretty clear that the model, this line, very nicely captures the behavior of this point data here for maybe the 4 measurements that would have been made. This is not that common in geological data sets. Very often you'll have much more scatter than this around some line, but you might still have some kind of generally linear trend. So if we have a set of points like this is basically 4 points that you could see like in an XY plot like this. It would be a pair of SiO2 values and temperatures. And we can fit a line using the equation for a line in the form that's shown here. So you've probably seen variations of this. I learned this as y equals mx plus b. I don't know what the preferred coefficient letters are for the math education here, but in the version that I found in a physics textbook, it was y equals a plus bx. And the a value here would be the value that corresponds to the y-intercept. So this is the point where this line would cross the axis at x equals 0. So where it crosses the y-axis at a value of x equals 0. And then b here is the slope. So you've probably seen something similar to this, maybe not in a little while, but you've seen it almost certainly in high school, and maybe it's come back in some form after that. So what we want to do is use this equation for a line and basically calculate the value for A, the y-intercept, and B, the slope, that best fit some set of values x and y. So we can take the same equation here, and we could say that if we had our best fit line, if we knew what A and B should be to fit our data set, for all the values of x we have, so in this case this would be all the weight percent SiO2 values that we've measured, we should be able to find what the actual value of the temperature was that corresponds to that weight percent SiO2 in the magma as best we can with a straight line. Now, of course, this looks very nice here. In this data set, you'll see in the data that we're dealing with, we're going to go back to the temperature data from the GeoPython course for the exercise this week. And suffice it to say, the data don't fall perfectly on a line like they do here. So doesn't mean we can't fit a line. It just means we have to make our best guess of what A and B should be. Now, if you're interested, there is a textbook. I think I maybe even have a copy of it with me today, if I didn't take it out. Yeah. So there's a textbook here. It's kind of a classic physics textbook called Introduction to Error Analysis. It's maybe not the most enjoyable thing you'll ever read, but as far as the topic goes, it's actually a pretty approachable description. It's not super heavy on the math, and it has good examples of like each different concept that we'll come across. The stuff that we're looking at today is basically chapters 8 and 9 out of this textbook. And if you're interested, I'll have the book up here and you could just take a quick look. I think the library has copies, at least a copy as well, but you're welcome to borrow mine if you're really dying to read more. But in there, they go through the complete set of steps that you need to take to come up with this equation for how you would calculate what the best y-intercept value is for your data set and what the best slope value is for your data set. I'm just giving you the equations here because I don't want to bore you with going through the steps of how we get from some set of data points like this to an equation for A that gives us the best y-intercept and B, the best slope that fits those data points. But if you're curious, you can find it in the textbook here, and it's not really so heavy in terms of the math if you're interested in doing that. But what we have more or less is just a way to calculate these two values. It depends only on x, or x squared, and y, and then some combinations of the two with various summation terms here. So if you're seeing these summations and having anxiety from last week's exercise already, we're not going to avoid them this week. Pretty much everything we deal with will have some form of a summation in it, and it's good to get some more practice with using Python to calculate these sums. So we have A and B, and then we have this delta down here. This delta is not really a special thing. It's just a shorthand so that the textbook author didn't have to write this extra term in the bottom, but could just put in a delta in place of this little bit longer thing here. So delta, again, depends, in this case, only on values of x, and summations of, for instance, x squared, and then the sum of all the values of x squared. These two things are different. This is the sum of all the values individually squared, and then this is the sum of all of the values of x, and then that sum squared. So I'll highlight that because you'll come back to this when you work on the exercise, and this is a subtle but important difference between those two sums. If these two terms were the same, of course, the difference between the sum of x squared and the sum of x squared would be 0, and it's not 0. So there's that. So yeah, these are the basically simple form of calculating this least squares regression. It does not take into account the uncertainties in the data. So you might think, like here, maybe we can measure the SiO2 content quite well, but maybe the temperature at which the magma was at is something that's a bit harder to measure, so there'd be some kind of uncertainty on that measurement. Typically that's the case. You might have a error bar on the y-axis values. That's not taken into account here at all. It's just the points themselves. If these are mean values, it would be just the mean values that are being fit by this line. And so this is what's called an unweighted least squares regression. So that means that there is no consideration of the uncertainty. We could calculate the same thing considering uncertainties if you wanted to. Oftentimes it's the case that you say, well, if I want to fit my best line here, I want to make sure that my data with the smallest uncertainties pull the line closer to those points, and the data with the big uncertainties don't affect the position of the line too much. That's pretty easy to do. Small modification to the equations that we have here, but we're leaving it off because we don't use it in the exercise, and there's no need to bury you in extra math. What's interesting to me is not necessarily always interesting to you, so I'll keep it to what we have here. So yeah, that's our least squares regressions, and again, this works pretty well if we have data that seems like a line will provide some kind of reasonable fit to the data. It's often the case that some other shape of a curve might provide a better fit to your data, and the question then is whether that curve makes any sense. If it's an exponential curve and you expect exponential behavior, okay, maybe that's logical, but if you fit a 10th order polynomial curve to your data because it fits really well, you don't necessarily have a good reason to do such a thing because there's not necessarily a physical meaning to a 10th order polynomial. And if you've played around with these kind of curve fitting things in Excel before, you've seen that basically as you make the polynomial number go higher, you can get a better and better fit to your data, but it might not have any physical meaning. In this case, the nice straight line is telling us that there is something about the behavior, that the temperature and this weight percent SiO2 are related to one another. And again, we know that going back to kind of first year geology courses. So yeah, any questions about this least squares regressions? Have you seen, I guess you probably haven't seen the math for this before, but I guess you've at least seen these kind of lines fit to some data before in some place, I assume, yeah? Have you done this before in Excel? Anybody? Yeah, some? So this is something that might come up in your thesis if you have measurements. You might want to fit a data, trend line to it. With our temperature data in the exercise today, we can fit a line that basically will allow us to say, on average, how much is the temperature increasing per year, or decreasing, or whatever. But that's the reason for fitting a trend line. In that case, is we get a nice number that says, okay, on average, it increases this much per year in our temperature observations. Okay, so that was topic one, and we'll keep it kind of short and sweet with that. On to number two, and this is linear correlation. So this might seem like kind of a, I don't know, not such an interesting topic, but this again comes back to something related to fitting our data to a line. And in this case, the question is, how well are these data fit by a line? And I mentioned earlier that often when you see a plot where there's some scattered data and there's a trend line fit to it, you'll see like an R value or an R squared value reported there. That's a measure of how well that data fits to a line. If all the points fall in a perfect line, then you get a value typically of 1.0 for R or 1.0 for R squared. If it's a straight line with a negative slope, you get a value of -1. So our values of this R that we're going to talk about for the linear correlation will vary between 1 to -1. And it's going to measure basically how well do our data fit to a line. I could explain that several times over, but I think actually the figure that I borrowed here from Wikipedia does, I think, kind of a nice job showing how these values of R vary for different kinds of data distributions. So if we consider just the top row here first, we've got an example here of a bunch of data points that all plot pretty much in a straight line. I guess you can kind of see that reasonably well. If not, you can take a look at the course page. And in this case, the data plotting all along a line with a positive slope gives us an R value of 1.0. That means basically we have a perfect fit to our data, or our data are perfectly linear with a correlation coefficient that says the data fall all on a straight line. As you get a little bit more scatter in your data, you would still look at this and probably say, yeah, I can see there's a trend in these data. And if you fit a line through here, you would see that you get a slope that looks similar to what we had before, but because there's a little bit more scatter, the points aren't all falling right on a line, we get a slightly lower value for this correlation coefficient, meaning the data are still pretty linear, but they're not perfectly on a line like we saw with the 1.0 value. And again, as you get to a little bit lower correlation coefficient, 0.4, you can see again more spread. Probably if you stand back and look at the data and kind of squint, you can maybe see that there's a general trend that there's still a positive relationship between the x and y values. You could put a line through there and say, yeah, that looks like there's some kind of relationship. But by the time you get to the 0 value, essentially here you have no correlation between the values on the x and y axis. It just looks like a shotgun blast, random points, and you could fit a line with any slope through here and have an equal fit to the data. In other words, there's no correlation between the y-axis values and the x-axis values. And the same thing basically happens if you kind of go in sort of a mirror here from 0 to negative values. Basically, we're seeing the same thing with negative correlation coefficients. That at 0.4, we've got a little bit of a correlation. 0.8, or sort of minus 0.8, we've got a stronger negative correlation, and then a value of minus 1.0 would be data that fall perfectly on a line with a negative slope. So that's basically how this works. I guess, have any of you seen this R-value stuff previously? Yeah, okay. So you probably get the basic idea then. I don't know whether anyone's actually calculated what these correlation coefficients mean, but this is a pretty fundamental statistical term, statistical concept, and it's used in all kinds of different data analyses. The second row is kind of interesting because it shows a little bit of this somewhat unexpected behavior here. I mentioned that if the data fall perfectly on a line, you get a value of 1.0 if the slope is positive, and minus 1.0 if the slope is negative. And you see that for the first 3 here, and the second 3 on the right side. For the middle case, you basically have no value that's listed there because the data are not in any way, although they're falling on a line, they're not sort of correlated in such a way that you could say there's a relationship between the values on the x and y axis. Essentially, we have values along a constant value in the y-axis and a range of x-axis values. So you don't get a slope here. In this case, you don't get a correlation coefficient value because the slope is 0. And if we look at the equation here, I think we can come up with a case that if the slope is 0, then this value will be undefined. So you have to be a little bit careful that as the slope gets shallow here in cases like this, even though the data are on a line, you may get no correlation between the two values. And then lastly here, if you've got these kind of random patterns, you know, data that's sort of in a wavy pattern or just like boxes that have been rotated, a little kind of smiley thing or whatever, all of these data have correlation coefficients of 0. And if you sat there and tried to put a line through the data, I think you'd see that exact situation. There is no line that really fits these data. They're all distributed in such a way that they're not really falling in a linear trend. If you had some other equation you were using to calculate your coefficient, maybe you could get it to fit something else, but it won't fit a line. And so all of these cases would have correlation coefficients of 0. So that's the idea in terms of the concept, and what we'll deal with in the exercise is basically doing exactly this. We'll fit our data, our weather data, with a trend line in the first part of the exercise, and then we'll calculate this correlation coefficient to see how well the data are fit by a line in part 2 of the exercise. Mathematically, the relationship here is not involving too much more than what we saw earlier. There's some terms here, x, these are basically just your values on the x-axis, and then the x bar is just the mean value of those values on the x-axis. And y, again, are the values on the y-axis, and similarly, their mean values. So there's a sum of this product of these two, and then this is divided by the square root of the sum of the squared differences between the x values and their mean in that case. So you'll get some practice putting this equation also into a Python function. If you're paying attention, you might recognize that this term here, I don't know why that just shut off. Okay. This is basically just the deviation. We saw this last week, and you might think, well, you told us last week that the deviation, if you sum all of the deviation values, is always 0. That's true. So if we summed all of these terms by themselves, we would expect to get a value of 0 back here. So you might wonder, like, well, how come r is not 0 in that case? And that has to do with the fact that this summation involves calculating the difference for value I along the x-axis and its mean, and then multiplying that by the difference with value y and its mean. So that's why you don't get this going to 0 here, is because the difference between some value of x and the mean value, and then the same point value of y and its mean is going to be something. It's not 0. When you multiply the two together, you'll get something different. So that's the summation not going to 0. I don't know whether anybody really kind of would have noticed that, but that's just in case you get curious about why this isn't squared or something like that, because that was the thing about the standard deviation last week, is it had to be squared so that we got some kind of meaningful value, and these values are not squared in this case. So anyway, we'll calculate this correlation coefficient r, and you'll add that to some plots in the exercise for this week. Any questions about this correlation coefficient idea? Okay, so if not, then let's go to our topic 3, which is about goodness of fit. So there are lots of different ways in which you can measure how well some data are fit by a prediction. We could think of an example here just to kind of give a graphical view to start of some age data. And perhaps you've got age data that were measured where you calculated the age and then there's some uncertainty. That's probably a combination of the analytical uncertainty. So the equipment you use to measure the age has some uncertainty in its age measurement. But also, typically what's done is you might measure the age of several minerals in a single rock sample and then calculate the mean of those measurements and their standard deviation to show how much the age uncertainty is in the reported age here. So you've measured something as the blue dot. You've got some uncertainty in the error bar there. And then we've got a couple different predictions. If you look at this, it's not too difficult to say that, well, this prediction over here, this white square that's within the error bar, is a pretty good fit to the data. It's within the uncertainty. It looks good. And the one over here is not within the uncertainty, and we might say, okay, well, that's not a very good fit. That's a sort of qualitative goodness of fit. Right, so we can basically say something like that that tells us, you know, roughly how well the data are fitting our measurement. But we can quantify this as well, and there's a lot of different statistics that can be used to measure something like how well data fit a prediction. We're going to deal with one called chi-squared, and maybe you've seen this at some point as well. If you had a kind of basic statistics course, you might have encountered the chi-squared value. But yeah, the general idea is the goodness of fit will tell us how well do our data fit some prediction. In the context of the exercise we'll look at this week, it's going to be how well do our data fit the trend line that we have fit to them, considering the uncertainties in the data, which is related to the standard deviation in temperature for a given season. So we kind of got the general concept here. Mathematically, there's a couple different ways in which this chi-squared term can be calculated. First is what's called the weighted sum of the squared errors, which probably means very little to most of us. But essentially, the idea here is that if we had some measured age, some observed age, O, and we took away or subtracted from it the expected age, so this would be in the context of the picture up here, our observed age would be the blue dot here, and the expectation or the prediction would be the white square. If you take the difference between those two and square that, and then divide by the standard deviation, that's one way in which you can calculate the chi-squared, which is the measure of the goodness of fit. Now, in terms of what that value actually means, it is a fairly intuitive statistic by itself. If you consider the case here of the difference between the observation and the measured value, or sorry, the measured value and the prediction, if you take the difference between those two and divide by the standard deviation. Standard deviation is basically going to be the error bar that you have here. As long as your point here, the square, is smaller than that standard deviation, you're going to get a value for your chi-squared that's less than 1. So whatever this standard deviation is down here, as long as this point's within the error bar, the value will be less than 1. If it's right at the edge of the error bar, the value you would get here would be equal to 1 exactly. And if your prediction and your measured age are exactly the same, the difference between the two is 0, and the chi-squared value you would get would be 0. Now this is not, I mean, the smallest chi-squared value you can get is going to be 0 because both of these terms are squared, so you're always going to have positive numbers or 0 for them. But there's no upper bound. So if your data fit the, if your prediction was off the side of the web page, way off to the right, you could have a very large chi-squared value because the difference could be quite large between the two, much, much larger than the standard deviation, for example. So again, if we were to consider the case of this point that doesn't fit our data very well, the difference between the blue and the square in this case will be bigger than the standard deviation. So if that's bigger and you square it and divide by the standard deviation squared, you should expect that this bigger thing on the top is going to give you a value that is greater than 1 for the chi-squared. So for an individual measurement, the idea here is that if the value is 1 or less than 1, we know that we're within the uncertainty of the measured age or the observed age with our model. If the value is greater than 1, we know that we're outside of the uncertainty for a single measurement. The thing that can become a bit tricky here is that you can see this as a summation. So if you have more than one measured value, let's say we have 3 predicted ages and all of them fall right at the edge of our error bar. So when we calculate the chi-squared value for the first one, we're going to get a difference here that's basically the standard deviation divided by the standard deviation, so a value of 1. And for the second age, if we do the same thing, we get a value of 1. Third age, we do the same, we get a value of 1, and you sum those together, that gives you 3 for your chi-squared value. Now, we know in this sort of hypothetical case that all of our data are right at the edge of our measurement uncertainty. They're all within the error bar, or right at the edge of the error bar, but we get a chi-squared value of 3, which is not necessarily intuitive because that doesn't tell you that for your 3 ages whether or not you're within the uncertainty. So for that reason, there is another version of this chi-squared equation that we'll work with in the exercise that is basically the same thing that we had previously, but then multiplied by this 1 over n term. So what this does is it kind of reduces this chi-squared value by the number of values that you have here. Now, if we go back to the case we were considering where we had these data that were all at the edge of the uncertainty, right at the edge of the error bar, so that the difference between the measured age and the expected value or the prediction was the same as the standard deviation. Now, if we get this summation that gives us a value of 3 for the chi-squared, we also divide by 1 over 3 because we had 3 measurements. And that gives us back to this chi-squared value being equal to 1, which is more like what we would expect in the case that all of our data are within the uncertainties. This value here that we get in this case, a value of 1 would tell us that in general, the data are within the uncertainties of the measurements that we have made here. Of course, values that are smaller than 1 would tell us in general that we're smaller than the uncertainty, so we have a better fit to the data. And a value of greater than 1 would tell us on average that the data are not within, or the predictions are not within the uncertainties of the data. Does this kind of idea make sense in terms of what the equation's doing here? I see some nodding. I sort of assume that this is somewhat intuitive, but of course you'll get a chance to work with it in the exercise. That may clarify things a bit. But I suppose at least the basic idea here of being within the uncertainty in your measurement as kind of a good fit, and outside of the uncertainty in the measurement being sort of a bad fit, that's what this chi-squared statistic is supposed to do. It's supposed to give us one number that allows us to see, okay, do we fit within the uncertainties or not, in general. Now, there are ways that this can be a little bit misleading, but we don't need to worry about that kind of case right now. We'll just keep it simple. And really the only noticeable difference between this first equation here and the second is that we just normalize it. We just divide by the number of data that we have so that this value doesn't keep growing and growing and growing as you get more and more data. You could have a huge number of data that all fit your data set really well, and the chi-squared number would be kind of misleading in the case of the first equation. So yeah, any questions about this chi-squared topic or things with the previous two least squares regressions or this linear coefficient correlation stuff? All right, if not, let's jump over here to exercise 2. The GitHub Classroom link is not yet live, so you won't be able to start that just yet. We'll make it live here in a moment. I prefer to get a second set of eyes to look over the exercise once before I make it live, just to avoid any typos. So I think Lotta has looked it all over and should be good to go, but just need to add the link back into the course page. But what you should be able to do is you can go and take a look at the exercise already. It's posted and available. It's 3 problems, so similar to last week in that sense. And one of the problems corresponds to each of the 3 topics that we just talked about. So there's something about linear data regression, and then there's something about the calculation of these correlation coefficients, and then finally this goodness of fit stuff. In terms of the data we're dealing with, we're going back to the data we dealt with in exercises 6 and 7 from the GeoPython course. So this is the weather data. In this case, I just took data from the Helsinki-Vantaa airport weather station there. So we've got data that starts in started collecting data in 1952. We've got data from 1953 in this case because I've calculated seasonal average temperatures, just like what you did in exercise 6 in the GeoPython course, if I remember correctly. So then in the course we had something like the year, we had the mean temperature for the winter season, we had a standard deviation for the winter, we had a mean for the summer and a standard deviation for the summer. I guess you guys also had like spring and fall as well, but we're only going to deal with summer and winter in terms of what we analyze here. The focus in terms of the exercise is basically to look at what are the trends in these data. So, we plotted them before, but now we can put this trend line in there. We can look at the slope and kind of get a sense of how much the temperature is changing year to year on average. And then we can also calculate things like, well, now that we have this line, how well does it fit our data? Do the data really, are they fit by a line? And then lastly, we can do this goodness of fit calculation, which is another measure of how well the data fit a line, but including, in this case, the uncertainty. So we'll take a look at that in just a second. So I've provided the data file for you. I've put a little note, I think, somewhere in here. Here, that if you want, if you're looking for a challenge, you can go back and reprocess the data as we did back in exercise 6 and 7 in the GeoPython course to produce this data file. But the thing to be a bit cautious with is that your data file values may be slightly different than the values here. So when there's things like it prints out, you should get this value for your goodness of fit, you might get a slightly different number if you process your data file yourself. So if you want to do that, I certainly would encourage you to do so, but just be aware your numbers might be slightly different than what the exercise says. So like when you test your functions, you should probably be okay, but your goodness of fit, your R values, things like that might be a little bit different. Okay, so pretty standard stuff here. We read the data file first, and in this case, the data file has nothing really fancy. You don't have to skip any lines. You don't have to specify a certain delimiter. You don't have to do anything special because all I did was I just dumped the data out of a pandas data frame to a file, and reading it back in means you just read it back in without anything that you need to do to that. So there's no date time index stuff or anything like that in this case. We're keeping it pretty simple. So read the data file in, that's your first step. Then you'll have your seasonal temperature values you can deal with. And stage one of dealing with the data here is going to be calculating this trend line, the slope and intercept of line that would best fit the data. And we'll do this for, I guess, 4 cases. So there's one for the summer, one for the winter. That's probably naturally sort of clear and obvious. But we're also going to calculate the same thing for the summer and winter, but only for the last 20 years. So we have the summer and winter trend line for the whole data range, which is from 1953 to 2019. And then summer and winter for the last 20 years, so from 2000 to 2019. So that'll be what we're doing in terms of the data that are being analyzed here. For the function, you'll make a function called linregress that calculates these A and B values. And this will return, the function in this case will return 2 values. We haven't dealt with that before, but there is a little hint here about that you can return more than 1 value with a single function, as long as you put a comma between the values. So there's normally you just have return and then some variable, but you can have return A comma B, and then that will give 2 values back. When you call the function, then you want to say A comma B equals linregress blah blah blah. You can actually see an example here that would test the linregress function. So I have A1 and B1 that are both going to come out of my linregress function because we calculate both A and B in that function. You could have separate functions, but it doesn't really make a lot of sense to do that when they both have this delta in them and so many similar terms. It's easier just to return 2 values. So you can see the test in this case because this is basically going to allow you to see whether your function works, and I think it's nice to know that your function is working properly before you move on to the next step, which is to calculate the seasonal regression line. So as I mentioned, you'll calculate for the summer and the winter, and then for the last 20 years, summer and winter, the slope and intercept of the line that best fits the data over those 2 time periods. So once you've done that, then there's a couple tests here that will allow you to see whether or not you've gotten the right values from doing that, those calculations. And then the next step is to plot your results. And I think maybe I can't click on this. Maybe if I do it like this, it's a little bit bigger. So what you're going to do is basically make a plot that looks something like this. I've used subplots here to put these both together on a single figure. You don't have to do that. You can make the plots separately. In fact, you probably should make the plots separately. And this one has the wrong title, so sorry about that. But you would have, in this case, something that looks like this for your data. You've got the values plotted with the standard deviation in temperature for the season as the uncertainty here. So each one of these points corresponds to 1 year for the summer mean temperature and its standard deviation. And then you've got your trend line here. That is the thing you calculate with your linregress function. And you plot that. And then you add some text that says what the slope of that line is in this case. So it's 0.028 degrees Celsius per year change in temperature over the data that we're looking at here. And same thing then you can do for the winter season. And they'll do exactly the same operation, but for a smaller data set in the second plot, where you look only at the last 20 years and see how the trends in terms of the temperature change may differ. So I guess that's the kind of basic for problem number 1. And I think the plotting is not too tricky. I think we've encountered most of the stuff you need to make this plot, other than plotting the line, and there's a hint about how to plot the line in the exercise hint for this week's exercise. I hope this link works. Of course it doesn't. So maybe I'll fix that before I make the exercise live so that the hint link works. Those are little things that never do. So it's suggested that you use something like red and blue for the colors. I guess I don't have a strong opinion about that, as long as you use something that's kind of a warm color and something that's kind of a cold color. And for that reason, I've included the link to the Matplotlib documentation. On there, there's this list of named colors, and if you scroll down the page a little bit, you can find here a whole bunch of different color options, and you can just give the name as the color when you plot with pandas, so that you can choose something if you like. You know, maybe you're a fan of orange instead of red, or something else like that. You can play around with the colors if you want to do nice pastels or whatever. As long as they're different and it's clear that one is kind of warm and the other is cool, and you're consistent, it doesn't really matter what colors you pick. You're free to choose things that look nice to you. I like these Tableau colors just because this is what Pandas is normally using by default. So I think that the sort of solid blue looks a little oversaturated, but this tab blue looks nice, at least to me. So, but you're free to pick whatever you think looks good. It's nice to have a little bit of artistic license in the exercise somewhere, because everything else is pretty rigid. So otherwise, yeah, if you want to know, there's also ways to put like little end things on the error bars. You might notice here that the error bar don't have the little end cap pieces on them, like you might often see. If you want to put those on, you can ask us. We can help you with that if you would like. This stylistically is supposed to be a better way to represent the data. It's makes it easier when you have a whole bunch of points close together like this to see the error bar if you don't have the end cap on there. I guess that's the logic behind that, because this did not used to be the default way of plotting in Pandas up until maybe a couple years ago. So you're going to make some plots, and then you move on to problem number 2. And the question here is, does this line fit our data well? And for that, we can calculate this linear correlation like we have already seen. So this is our correlation coefficient function that was in the lesson already. You're going to convert that to a Python function that will return a value r when you give it some array values x and y. So you can do this a couple different ways. If you pass in x as like a NumPy array, if it's coming from Pandas directly, you can pass in x dot values, and that will be a NumPy array, which means you can do things like calculate the mean with just x dot mean. Or if you want to use your mean function from last week, you can copy and paste that in here and use your mean function from last week and do things the way that we did the week before. Not restricting you to having to use your mean function like we did last week. So if you want to use the NumPy way or the Pandas way of doing dot mean to get your mean values, you can certainly do that in this case. I don't think there's any of these tests that check to see whether or not you've used NumPy. So you can do that if you like. So you'll calculate the r values. Then there's the tests, of course, that go along with that function. Then you'll calculate for each of these different times what the correlation coefficient is. So you'll have one for the winter, one for the summer, and then one for the winter in the last 20 years and one for the summer of the last 20 years. And then there's a couple tests here that will print out some values, so you can check again to see whether you've gotten the right values for your correlation coefficients. Then it's round 2 of the plotting. And in this case, what you're going to do is plot the same data from exercise 1. Basically, if you want to copy and paste your plots, that's probably not a bad idea because you'll make a couple small changes. But the main thing is we're going to take the same plot that you would have made back here. And with this plot, the difference is this time we're going to take off the uncertainty, the error bars that are on here. Because when we do this correlation coefficient r, it doesn't consider the error bars, so it's good to plot things without the error bars so you can see visually how well the line fits the dots. So all the points here, how well do they correspond to a line? Because you're going to then add in text instead of the slope like we had in problem 1, you'll add the correlation coefficient that you've just calculated. So you put that text on there, and you can see then the number that says how well the data fit, and you can also look and see visually how well does it look like our data fall on this straight line. So again, the plots are similar enough to problem 1 that you'll probably want to just copy paste and then edit those as described in part 3 here. Probably this link doesn't work, so I'll fix that link as well before we make the exercise live. Right, let's go then here to problem number 3, where we calculate the goodness of fit. And in this case, we are now going to consider the uncertainty in terms of trying to figure out how well this line fits our data. We use this chi-squared equation that we saw in the lesson just a little bit ago, but we use the version that's normalized, so you get the 1 over n term out in front, and then the difference between the observed and expected values. The observed values in this case will be our temperature data that we have. The expectation would be at each one of the points what the temperature would be according to our trend line. So that's actually a relatively easy thing to calculate because we have the equation for the line that says, okay, for any x and any y, or sorry, for any value of x, so any year, we should be able to calculate what the value of y is, which is the temperature in this case, because we know the slope and we know the y-intercept. So what you'll do is you'll calculate the values of the temperature that's expected according to the trend line for each year, and then you go along, basically sum up the differences between the observed temperature in that year and the expectation based on this trend line, and then that's divided by the standard deviation in the temperature for that season. Sum all those up and you'll end up with a goodness of fit value. And well, okay, we start with our equation for the chi-squared. Again, you can see the tests here to make sure your equation works. And then we calculate 4 goodness of fit values as you would expect. 1 for the winter, 1 for the summer, and then those same 2 values for the last 20 years. After that, you're basically done. There's an extra cell that's just tucked in here that allows you to print out what your goodness of fit values are, so you can see them all together in one Python cell. And at that stage, there's a few questions for you to answer, and that's that.